This is lecture 26, a continuation of friction in chapter 8. And in this lecture, I'm just going to go over a few more examples of friction. I wanted to bring up a couple things though. One is that I think it's 8.2 of your book, we do talk about what are called wedges. And it's not a really difficult concept, but it's something that takes a little bit more time than we have left. And I know for a fact that we're not going to cover it on the final because another instructor didn't cover it at all. And although it's interesting, I think that you guys will be better served not having to add that extra amount of information to your plate. So we're going to forego that. So you may recall in the previous lecture, I talked about what's called the angle of repose. And that's just a shortcut of combining the reaction with normal force and the friction force into one. That will still work in some problems, but I would say that don't worry about using the angle of repose. It's kind of like a force triangle. It's a red-haired stepchild that doesn't necessarily have to be used or acknowledged. And so just go ahead and follow the examples that I've shown you and you should be okay. Okay, with that, I want to show you this first example. Now, in this one, we have a cabinet, and it's on casters, and let's assume the casters are locked, so they're not freely rolling. And we're going to push the object. Now, one would ask, why not just unlock the casters? But let's say that the casters are frozen in place. And this actually happened at a Jamba Juice where the casters were frozen in place because of corrosion due to the juice that came out of it. It actually seized up the casters, and someone pushed it working there, and it fell on one of the employees and ended up with a lawsuit. So point is, this was an example of where friction was not your friend. But let's imagine you have this cabinet and you're trying to push it and it's locked in place. So how are we going to do this? Well, we know that if we apply force P, that the thing's going to slide at some point. But the question then is it going to slide or is it going to tip? Now, you can imagine that if you push, just from experience, the higher up you push this towards the top, the more apt you are to tip it versus slide it. So let's look at this and figure out, well, how much force is it going to take? So we know that the cabinet itself is 4.5 feet high. Actually, I'm sorry, H is 4.5 feet high. The total cabinet is 6 feet high. But really, we're just interested in where we're pushing it. We know that it weighs 250 pounds, and the static coefficient of friction between the casters and the floor in the locked position is going to be 0.4. All right, so here's our cabinet. And so we have 1.5, those are feet, because we know the center of gravity is somewhere right here. Now, the vertical component of center of gravity, or where it physically is, isn't really relevant here. We want to know more where it is in terms of the x direction. And that's because this vector goes infinitely in this direction. So there's our 250. Now, we want to determine the maximum amount of P without movement, either sliding or tipping. So let's look at our free body diagram. We know we have a normal force at A, normal force at B. We also have, we can say, friction force B and friction force at A. Now, we can model this system in this context as being NA and NB as one normal force, meaning that we know that if you add the total weight of it, that the normal force A and B is going to be 250 pounds. The differentiation is an important point. So the maximum friction force that can be generated then, we know is just going to be the coefficient of friction multiplied by the weight, which is going to give us 100 pounds. So we know that if we apply a load of P or greater here, then it will slide. Anything less than P, it won't. So we've determined that that's the maximum P without movement, but we haven't checked tipping. So now let's look at tipping. Now, if you picture this thing tipping, then the criteria is going to be for this NA to be 0, kind of like in that the half pipe that we looked at in the last lecture. So all of the load really is going to be on NB, because NA, if it goes to 0, that means you're starting to tip. But so what we can do is we can simply sum the moments about point B. And if we do that, if we sum the moments about point B, 0, what we're really looking for is what force is required for tipping to occur. And if that's the case, then the only force that's really important in this context is the force here and P, because what I've done is I've added NA and NB together in this context. So what do we have? And what I mean added together is that because I'm assuming that tipping occurs when NA goes to 0, NA is not going to contribute to the moment. So the only 2 points that really matter are NB, or B, and P. And so we have the 250 is going to be balanced with P, because NA being 0 isn't going to have any contribution to the moment. So if we do this, we have essentially minus P times 4.5 plus 250 times 1.5 equals 0. So 250 counterclockwise, P times that. And what I end up with is P equals 83.3 pounds. So what that tells me is that if I apply 100 pounds here, it's going to slide, but before I even get to that, if I get anything above 83.3 pounds, it's going to tip. So the maximum load, we have to take the more conservative of the two. The maximum load that can be applied is going to be this 83.3 pounds. Now, if I asked you, well, where could you push it? Where could P be applied so that it wouldn't tip and it would slide instead? We already know it'll slide at 100 pounds. So what we could do is we could rewrite this as minus, if we then sum the moments about B again to 0, because still the same criteria, we don't want to tip, so NA doesn't count because it's 0. And so we could say minus 100 pounds, because we know that's the amount, we know the 100 is going to be the amount of force that'll make it slide, and then multiply that by the y distance, which is the unknown, and then that's going to be plus the 250 times 1.5. And that all equals 0. So for that, we get a y of equal to 3.75, which is essentially 3 feet 9 inches. All right. So if we push at 3 foot 9 inches, then it'll slide. If we push below it, we know it won't tip. So as long as we're below that height when we push it, it'll slide at 100 pounds. Okay. So that's just looking at the comparison between moments and sliding. Let's look at another example. So in this one, we have our 300-pound gremlin, or I'm sorry, 3,000-pound gremlin. And in this context, we're going to be pulling a log. And what we want to know in this problem is how much force is going to be required, or I should say how much force, but what is the maximum weight of the log that we could pull before we'll sit and spin, so to speak. So the first thing we want to do is figure out how much is what is our maximum friction force, right? Because we have this car, and we know how much it weighs, and so we know how much friction is going to be generated, maximum friction between the ground and it, and then from that we can use it to calculate the maximum amount of the actual log itself. So let's go ahead and do that. So again, if you want to try these problems on your own, by all means do. But I know that these friction problems are fairly new. So what I would probably recommend, especially because this is a good problem, this would be a good type problem for the final, is to go ahead and, all the ones I've done would be good, but this one is what I'd say is a typical one that I don't think we've given it on the final before, but it's similar. Anyway, I would look at it and I would say, how do we do the problem? And the more you can try to figure it out yourself without my help, the better off you're going to be. So think about how you're going to do this one. You have A and B points, and ultimately you're going to figure out what is the maximum amount of tension that can be created in that rope before that car starts to spin. And so once you know what that tension is, then you can then backtrack and figure out how much that log has to be passed away. So let's go ahead and look at this. So here's our free body diagram. So we know that here's our log, mass of the log, the tension on the rope connected to the car, the normal force on the log, and the friction force of the log. And then we look at our car, and we know the center of gravity is up here. We're giving it at 1.6 and 1.2 meters relative to the front and back wheels. We know that we have a normal force at A, normal force at B, friction force at B, friction force at A. The other thing is we know that the torque, the tension of the rope is not at the ground. So if the tension's big enough, you can see that you could almost do a wheelie. If the back was able to stay stuck and it had enough, if it could dig in infinitely, so to speak, but say the log was too heavy, then you could actually the car would actually take off. You'd actually rotate about the back axle. So that's something else we may have to consider. But let's just look at it and see how it goes. So we have this. So now we know that our force of friction is going to be 0.4 times the normal force A plus B. So the first thing we need to figure out is this thing going to tip? So let's first figure out what our tension is. So there's 3 steps to this problem. One is, what is the maximum tension that can be created? The second is, will it tip? And what I mean by tip is, will it wheelie? And then if it won't, then the mass of the log. Okay. So if, like I said, if it wheelies, that means NA is going to be 0. So we're going to have to figure out what that is. But let's first figure out what the tension is, assuming this thing's able to go. Again, it's 4-wheel drive, so we know that neither wheel is going to, are both going to add force to it. And we know that it has enough engine to spin the tires if necessary. So really what we're looking at is, what is the maximum friction that can be created? Because if the tires spin, that doesn't do us any good. So we know that if we sum the forces in the Y, we get the normal force A plus normal force B minus the weight, 3,009.81. So we know that that plus that is 29,430 newtons. Good so far. So let's go ahead and sum the forces in the X. If we do that, we know that the total friction is going to be FA plus FB, which we know is going to be mu static times NA plus NB. And we already know that NA plus NB is 29,430. So 0.4 static coefficient of friction times that minus T equals 0. So we know that the most tension that we can create is 11,772. If we, because that's the most static friction we have. Again, that means the wheels would start to spin otherwise. If this log is such that the tension created here is greater than that value, this thing is going to spin. So we're kind of working backwards because we're trying to find how big a log can it be. So if we had told you, say this log weighs 2,000 kilograms, then you would have then compared the tension created by the friction of the log to what you could do, calculate here, and you'd compare the two and say, well, no, it's spin or it would. So you can see how there's a lot of permutations of these types of problems, the way we can do them. We can ask a lot of different things. And so that's why knowing just how to do this one problem through isn't enough. You have to understand, what are we really asking? How are we approaching this? We're looking at friction as it relates always to the maximum friction. And that's the important concept. So as I said, we got to figure out, is the thing gonna wheelie? Well, if we sum the moments about the back, B, then if it wheelies, NA would be 0 or less than 0, which, as I said, has no physical meaning, but it gives you, it tells you what's going on, that it is wheeling. So sum of the moments, we know NA times the distance 2.8, that's the distance to B, 1.6 was 1.2, plus the tension times 0.5. Both those are going in the counterclockwise direction, and then minus the mass, or the weight of the car times its distance. And so we solve and we get that equal to that. So that means, since that's greater than 0, then that's good. That means that we're not going to wheelie, that tension isn't great enough to make the car wheelie. So now the problem's pretty much done, because now we just look at the log. And so we go back to this up here, we see that we know that tension is we're just going to basically set tension equal to this and solve. So we know that normal force, if we sum the forces in the y, we know the normal force of the log is going to be equal to, or the sum to 0 of the mass of the log times gravity. So we know that the normal force is equal to gravity times mass of the log. So we come down here and we say, well, sum of the forces in the x, that's going to be the tension minus the friction force. Well, what's the friction force? It's the coefficient of friction times the normal force. So we plug that in and we solve, and we get a mass of 1,500 kilograms. So we know that anything more than 1,500 kilograms is not, the car is just going to sit and spin. So there's another problem like this where we say, instead of having a four-wheel drive, we have a front-wheel drive car. And so the difference with that then is now you no longer have any contribution of friction from this, because rolling friction, such as like a wheel rolling down the street or on the road, is much, much different than static friction. So it essentially goes to 0 in that context. So that's how you do that problem. So that's one more example. So let's go ahead and go back. I have a couple more to show you. This one's a little different, but let's go ahead and go through this one. If you want to pause at this point and try this problem out, by all means do. Now, if you look at this problem, you have this drum moving, and you're given that it has a moment on it. And now think of it as you're just trying to hold it still. You're not trying to slow it down, because that would be a different dynamic. If the thing was already moving and you're trying to pull down and stop it, then you'd have kinetic friction, and it would be a different problem. More so is think of it as you're pulling down, you're hanging off of it or whatever, and there's a torque attached to it, and you're trying to figure out, what do I need to do to keep this thing from start moving? So we know we have a 35 Newton meter moment trying to spin it counterclockwise, and we know the coefficient of friction is 0.4. The drum has a mass of 25 kilograms, which actually turns out to be kind of a red herring in this problem, because you'll see, but sometimes you don't need all the data they give you. So don't feel that, try not to be too sneaky like that, but if you do end up with a problem where, for whatever reason, mass wasn't used, that's not that uncommon in friction problems. Oftentimes friction is independent of mass in certain ways. So let's go ahead and look at this. So here we have a free body diagram. Now, so here's our load P. We know that, and what I've done is I've separated the two. So the top is the bar. We have our reaction A, Y, AX. We know the distance is 0.5. We know this distance is 1 meter. And we know that the normal force on to the bar is pushing up, and the friction, because it wants to rotate counterclockwise, the friction is going to be opposing that motion. And then on the bottom, we know that if we look at the roller, it's going to, actually, I guess it's probably easier to explain from the disc. So the drum, we look at the middle of it as OX, OY. Those are the reactions because it weighs, it has a certain mass, and it's sitting on some kind of a mounting pin. The moment itself is going counterclockwise. So that means that the friction opposes that, because sometimes it can be confusing to see which direction friction is going. But we know that if friction's going to the right on the drum, then it has to be equal and opposite on the actual arm. And so that's why it's pointing to the left on the arm. And then, of course, the normal forces being equal and opposite. So here we have our mass. So I went ahead and said 225 kilograms times gravity, 245 newtons. And we know it has a diameter of 125 millimeters. So first thing is force on B. So it's maximum friction. So we know it's going to be mu static times NB. So it probably makes sense is to try to figure out what is NB. If we know that, then we know how much P we need, right? Because we could then sum the moments about A and calculate that. So let's look at this as we go. So if we go ahead and sum the moments about A, what do we get? We get P times 1 meter minus the normal force B times 0.7 meters plus the friction force at B times 0.5. So then if we go ahead, because we're on the verge of motion, we go ahead and substitute in the friction force for the mu times the normal force. So we get P minus 0.7 times normal force B, and then we get 0.5 times, and then what we've done is we've taken the normal force and substituted it, normal force times coefficient of friction for that, and that gives us 0. So if we go ahead, we know that P equals 0.5 NB. Now, that's our first equation. And that's just solving this, right? 0.7, that's negative 0.7, and that's 0.2, right? And so we end up with 0.5. 0.7 minus 0.2, 0.5, complex math, there we go. So we know this relationship here. So then, this is something where experience will show you and practice, but if we want to calculate because in order to do this moment up here, we need to know this force B, right? We need to know that, because if we know this, then we can solve for P. So we've already established what P is in terms of NB. Now we need to figure out what FB is. So we have no way to do that for just summing moments. That's not going to help us on A. But if we go back to this one, if knowing this torque, we can then determine what force of friction is going to be required to essentially nullify that torque. So sum the moment about O. So O is the center point. It's also convenient because it gets rid of the normal force at B, it gets rid of the weight, and all we're left with is that torque, and then that's going to be opposed by the friction force times the radius. And so we have 35 Newton meters minus the positive facing, or the clockwise facing friction times the radius. So we know that in order for this to not move, and it wouldn't matter if it was friction or if it was just a rope attached here, that it would take 280 newtons to prevent a 35 Newton meter torque from spinning this. So now that we have that, we can go back, and we take the normal force at B, because we know the friction force at B. We know that if friction force is mu times N, then normal force is friction divided by mu. So we get 280 minus that, we get our normal force is equal to 700. And so now we know it's 700. We go back in and we can solve for P, and P ends up being that half. So ultimately, that's what? 350 newtons. Okay, and that's that. So now this OX and OY down here that I have, sometimes the problem will ask, what is the reaction at O? It'll also sometimes ask what the reaction at A is, but I didn't care about it in this problem, but that's why that number is down there, because I wasn't sure where I was going with this when I wrote this out. But the 350 newtons is your value. And so because again, we were able to relate P, the amount of P we needed, to the normal force of B. And because of that, we were able to solve for our friction force and ultimately that. So hopefully that was clear. Again, not having you guys in front of me makes it difficult to see if you're shaking your head in understanding or shaking your head in complete loss and hopelessness. Hopefully that's not the case. All right, so I have one more example I want to show you, and that will pretty much conclude our walk through friction. And this is another good problem that I've done, and this is another good problem that can have very numerous types of permutations on, and is also a good type of final problem. And so in this problem, what we're going to do is we look at our structure, not our structure, but our system. And what we're trying to determine is what is the friction coefficient under A so that B doesn't come sliding down. Now, you can imagine that other ways to do this problem is we could give you the mass of A, or we could apply a force to A and give you the mass of B and say, well, what force at A would be required to push B up the hill? What's the minimum friction at B to keep it from sliding down? What's the minimum friction at A to slide down? We could add weight to this lever here, or the member that's connecting the two. So again, it changes the way you approach the problem, but it doesn't exactly change the way that the fundamentals. So again, we want to know what is the minimum friction coefficient under A. And so, and I wish we were doing this live so that I could set up multiple problems next to each other to show you. But whenever you have something like this, and this kind of goes back to the log and the car problem, you notice that when we were trying to figure out the maximum weight of the log, we looked at the truck first. And so we always start with what we know the most about, and we leave the unknown, or the one we're trying to solve for, is last. So with that in mind, which one are we going to start with, A or B? Well, we're going to start with B, because we know the mass of B, we know its friction coefficient. So what we can do is we can figure out what force has to be in that lever to hold it up. Because if you isolate the problem, imagine, if you were to take a cut through the problem and you just had, say, your hand holding B up, or another lever or anything, it doesn't matter if it's friction. There's going to be a certain amount of force applied to this rod, we'll just call it C, in order to hold B up. And so once you see that that can be determined, then you can just use the laws of friction, then figure out what amount of force is needed to hold that up. So let's go ahead, and again, if you want to try this out yourself, by all means do. But if not, then let's go ahead and do this problem. Okay. So here we have block A, block B. You know, block A weighs 40 kilonewtons, block B weighs 30 kilonewtons. Here's my 60-degree angle. I know that I want to know mu static under block A. I know that under here, mu is equal to 0.2. So I've drawn each diagram. So this one at 60 degrees, I know that normal force is always going to be perpendicular to the surface. My weight is always going to be straight up and down. And C is going to come in at that. Now, I know that this angle here is 30 degrees. And the reason I know that it's 30 degrees is if I look back up here. Now, if this is 60, that has to be 120. So if I were to create a triangle here, draw a line there, draw a line there. If that was 120, that's 30, that's 150. Therefore, that has to be 30 to be 180. So that's 30, and that's also from the geometry too. But so first thing I'm going to do is I'm going to look at this, and I'm going to figure out what is my value of C, because that's what I want to know. Because once I know C, you could probably see, no pun intended, that how when I go back over here, that I'll be able to solve for FA and NA, and I know the ratio of those two gives me mu. So let's go ahead and look at that. So if we look at block B, and in this case, we're going to, again, tilt the axes. So I'm going to tilt the axes so that it looked like this. So that's my X, that's my Y, tilted along this. So N is going to be strictly in the Y-axis. So I'm going to go ahead, sum my forces in the Y to 0. And I know that this is the normal force at B. So I know my normal force at B is going to be equal to 30 kilonewtons, right? But 30 cosine 60, because it's coming in, you know, if I think about this angle here, that's 60 degrees, and plus C times the sine of 30 degrees. And so it's easier to see if you tip it this way, you can see that the sine, that's my sine 30 of C, and that's my cosine of the weight of 60, and that's opposed by N. So there we have it. So if I simplify that, I get normal force at B is equal to 15 plus 0.5 times C. And that's just simplified. Now, I also know that my friction force, B, which is pointing up, that equals mu B times NB. Or I can write friction force at B equals 0.2 times 15 plus 0.5 C. Or friction force B equals 3 plus 0.10 C. So all I did was do some simple substitution, and there I'm done. So now let's go ahead and sum the forces in the X to 0. If we do that, then we know that we have the force B. And again, we did this because we knew that relationship, but now, and you can kind of see where this is going, what I want to do is I want to solve for C ultimately. So what I'm doing is I'm taking my Y components to get that, and then I can substitute it in down here. So I know in the X direction, I have force of B plus C cosine 30 degrees. And then that has to equal the weight going the opposite direction, or 30 kilonewtons times the sine of 60 degrees. So I plug in 3 kilonewtons plus 0.10 C plus C times square root of 3 over 2 equals 30 times square root of 3 over 2. And so now I have everything in terms of C. C equals 23.79 kilonewtons. And so that's the majority of the problem at that point, because now that I know C, I can come back and walk you through this part. So now I know how much C is, so I know C has to be doing here. So if I sum the forces in the Y, I know that the normal force at A has to equal 40 going down plus C sine 30. That's just a balance. So I could set everything equal to 0, but I think you understand at this point it's the same thing. So therefore I substitute in my value for C. I get a normal force equal to 51.895. Then I'm going to do the same thing for FA. I want to find FA. Well, I know FA in this case is just going to be equal to cosine 30 degrees times C. So I end up with 20.6. So I know that mu static, therefore, is equal to FA, right, over NA. And that's just the definition of mu static. So it gives me a value of 397, or essentially 0.4. And so never give a coefficient of friction to more than 2 decimal places. They're just not, they're rough numbers. They're not known that well. Generally 1 decimals is okay, but 2, you can do 2, but no more than 2. All right. So that's the examples I wanted to show you. So with that, I've covered pretty much every type of friction problem that you might see on the final. Now I did post a homework assignment that has some problems out of the book. I would look at those. The solutions are there. I realize there's not a lot of time left, but if you have a chance to look at those, I'd absolutely recommend it for the final. Along with this, you should be in good shape. But, you know, think again, you know, we're not going to look at wedges in the final. So typically the types of problems we see look like this, or the log being towed, or, you know, you can picture, you know, something like this where you have this and this, and then the weight hangs off, and you're asked, well, how much weight is there needed before this will start to move? And so these types of problems will actually be carried on in dynamics only with pulleys, and they get a little more difficult, but in there you can have them on frictionless surface or friction surface, where then instead of calculating when they start to move, which is fairly easy, you start to calculate what the acceleration is. So set everything to MA. And after you do a few of those, they're not really that terrible, but they're not really easy either. They're definitely a step up from what we're doing in this class. All right, so that's that for, so this is my last lecture of the quarter in terms of new material. I will have one more review lecture I'll give that I'll record that'll just kind of go over some highlights of the quarter and things to expect for the final. So hang in there, and I'll see you in office hours.